Okay, let's use mathematical induction to prove this sum always works no matter the value of n, as long as n is a positive integer. So proof will be by induction on n. First, we start with the n equals 1 step. On the left-hand side, if I have only one term on the left, then it'll just simply be 1 times 2. On the right, if n equals 1, I would have 1 minus 1 times 2 to the 1 plus 1, again replacing the n here by 1, plus 2. And this works because I have 2 is equal to 0 plus 2, so this is true. So the base case of n equals 1 works. N equals k, we'll assume that. And everywhere I see an n are replaced by k, so 1 times 2 plus 2 times 2 squared plus 3 times 2 to the third up to k times 2 to the k is equal to k minus 1 times 2 to the k plus 1 plus 2. So that's going to be my induction hypothesis. Lastly, let's use n equals k. So the left-hand side is going to look an awful lot like the line that's here, 2 to the third. Then I have my k plus, or k times 2 to the k, and then my last term will now be k plus 1 times 2 to the k plus 1. My target that I want to show this is equal to is going to be equal to, and let me put space here at the bottom, that'll be equal to, my target's going to be everywhere I see an n, I replace by k plus 1, so k plus 1 minus 1, so that'll be k. Everywhere I see an n, I replace by k plus 1, so 2 to the k plus 2, then plus the 2 at the end. So if I can somehow end with this, then I'm done. Okay, now by induction hypothesis, the first few terms, the part that I've underlined, is equal to this. So k minus 1 times 2 to the k plus 1 plus 2, then plus the extra term that's coming along for the ride. So this is by induction hypothesis. This term just matches the extra term over here on the right, and this is true by induction hypothesis. Okay, now we need to somehow simplify this. And one thing that I can do to simplify, certainly the plus 2 ought to stay put because there's a plus 2 here. So I'm not going to touch this. These two things have a 2 to the k plus 1 in common, and so I can factor that out. So k minus 1 off this. This one has a k plus 1. I'm factoring out the 2 to the k plus 1 that's in common. And then the plus 2 I'm just going to leave on the side to match this one down here. Okay, so this is equal to minus 1's cancel. A k plus k gives me 2k. So 2k times 2 to the k plus 1 plus 2. Okay, so to finish this off, I notice that this is k times 2 to the first times 2 to the k plus 1 plus 2. And then combining the exponents, I can add. So 1 plus k plus 1 is k plus 2. And so I've ended at my target, and that is the end of the proof.